In our final examples, we look at some special products that are a piece of the puzzle of the factorization process. Like I said, you want a comprehensive plan. You got to have a whole entire scope and sequence of what you're going to do, but you're going to learn it in small pieces. So here's the final piece that we're going to look at in the factorization process. And there's some other pieces that come in later that we'll pick up as the year continues. But step-by-step guide, look for your greatest common factor. If you have it, pull it out. Then go to your second step, which says, look to see if your remaining polynomial is a difference of two perfect squares. That's a special product that they're talking and referring to. So a difference of two perfect squares is pretty simple to recognize. Number one, it's only going to be a binomial. And these two numbers have to be perfect squares, and there must be a difference, means that it must be a subtraction sign. So the difference of two perfect squares should be relatively easy to recognize. It's much different than the others. It's only a binomial. It has perfect squares on the end, and in the middle we have a subtraction sign. So we've got to make sure that we are qualifying what a perfect square is. Perfect squares are things like this. If you do just generating numbers, 2 squared is 4. 4 is a perfect square. 3 squared is 9. 9 is a perfect square. 4 squared is 16. So 16, 9, and 4 are examples of perfect squares. They could be numbers that are sitting here and either in the a squared or b squared. The other things that are perfect squares that you got to be alert for is they have a squared. That is the same thing as a times a. A squared is a perfect square. You could have x squared. Well, that is x times x. Anything that is squared is a perfect square. And you can go and take it out a little bit farther. You can say x to the fourth is a perfect square because it is x squared times x squared. X to the sixth is a perfect square because it's x cubed times x cubed. Anytime this power is even, it is the result of a perfect square. So you got to keep in mind what perfect squares are and be on the lookout for them. So here's a piece of the puzzle. If you have a difference of two perfect squares, they can be factored relatively easily into this factorization pattern that you're seeing here. A plus b times a minus b. We'll have an example or two of perfect squares coming up, so I'll dive into that. Just try to figure out what it looks like. The second thing is a perfect trinomial square. So we may not see it greatest common factor. It's not a binomial, so we'll go down here, factor into two binomials. It's a trinomial. Trinomials factor into binomials. So what we're going to be on the lookout for is perfect square here and a perfect square here. Look at the ends. When they have a perfect trinomial square, we'll have perfect squares on the ends, but on the inside is going to be double the product of a times b. So the perfect square of 4 is 2. The perfect square of x squared is x. The perfect square of 25 is 5. So it's 5 times 2. Then you've got to double it, and that'll give you 20. So that's what they're looking at. It's twice the size of whatever the perfect square of a squared and b squared is. So we're looking at special products, trinomials that are perfect squares, and binomials that are perfect squares. So we're going to do some factoring on those. So I already kind of looked at problem A there in example 4. What I'm looking at is a perfect square and a perfect square. And if I double the 2 and the 5 and take it times 2, I get 20. So that leads me to believe this is a trinomial square. And you simply take the perfect square of 4, which is 2, and the perfect square of x squared, which is x, and you put 2x and 2x. You follow your sign rules. Anytime that is positive, the signs must be the same. Take a peek to the middle, and it's telling you they must both be positive. So plus, plus. The perfect square of 25 is 5, so 5 and 5. This should be our factorization of our perfect square. Now I want to come back here and do the FOIL. First terms multiply together. 2 times 2 is 4, and x times x is 4x squared. Do the outermost ones, that's 10x. Do the innermost ones, that's 5 times 2x is another 10x. And you do the last terms, it's 5 times 5, which is 25. And here's where this doubling effect always occurs in our perfect trinomial square. You got 4x squared. These two will always be identical because these are identical factors. Your outside and inside. Your outside and the inside will be identical, and you'll have 2 of them, so plus 20, x plus 25. So our factorization is 2x plus 5 and 2x plus 5. Okay, so it's a game of recognition, looking for special products, looking for monomial factors, looking for trinomials factoring to binomials. So here it is once again. I know I've got a 9 sitting there, and I got a 16 sitting there. 9's a perfect square, 16's a perfect square, and any even power is a perfect square. So I want to break it down into two binomials. The perfect square of 9 is 3, so 3x and 3x. The x squared is a perfect square of x and x. 16 is a perfect square of 4 and 4. Now I look at the sign. I'm going to do my sign test. It's positive, but my middle term is negative, which requires both of these to be negative. So it should be 3x minus 4 and 3x minus 4. Sometimes what they'll ask you to do is write this as a 3x minus 4 squared, just using exponents to help simplify it. Okay, so the next thing we're going to look at is the other special product. These are pretty obvious because it's just a binomial. This is much different than what we've been looking at in the previous examples. There's no greatest common factor, and you got x squared minus 4. X squared is a perfect square, 4 is a perfect square, it's a binomial. These factorizations always have the same factorization pattern. The perfect square of x squared is x, and so x times x. The perfect factorization of a 4 in a perfect square is 2, so you got a 2 and a 2. Use your sign rules again. Anytime this last sign is negative, then these signs inside your binomials have to be different or opposite. So one has to be negative and one has to be positive. The reason that has to occur is when you do your last term in FOIL, it has to give you negative. And the only way you get a last term that is negative is by having opposite signs in your binomial. So x plus 2x minus 2 is your perfect factorization, or the factorization that difference to perfect squares. Okay, so let's go to the next example. X squared minus 144. It's just a binomial, perfect square, and 144 is a perfect square. So your factorization process is always the same on the difference of two squares. Square root of x squared is x and x. The square root of 144 is 12 and 12. The last sign is negative, and the difference to perfect squares, they'll always have to be plus and minus because your last term must be negative. X plus 12, x minus 12. Final example in this is 36y squared minus 16. There's a couple different techniques you can use here. Like I said, I'm always on guard for greatest common factor. When I look at a 36 and a 16, I see a common factor. The greatest common factor of 36 and 16 is 4, so I can factor out a 4. And that's going to give me a 9y squared minus 4. So I factored out a greatest common factor. So then I look at what's remaining. After I factor out this greatest common factor, I should be looking right in here to see if it factors again. And what I recognize is this is a difference of two perfect squares. So 4 stays out there. It's part of your factorization, but we can factor our factored form again, this difference of two perfect squares. 9 is a perfect square of 3. Y squared is a perfect square of y. So we got 3y and 3y. The signs are going to have to be different, plus and minus, and the perfect square of 4 is 2 and 2. And this, if we want to write it, like I said, sometimes they may show solutions as an exponential, so 3y plus 2 squared. So there's quite a bit to put together here, small little pieces to try to build a comprehensive plan so that you know the entire scope of factoring, but you got to break it down into pieces and put them all back together so that you can factor completely.